So now we'll look at the equations that are necessary to successfully design an EmDrive cavity. And we start off with perhaps the two of the most famous equations in physics. The first one, Formula 1, is Newton's force equals mass times acceleration. And equation 2, which is Einstein's E equals mc squared. Now we need Einstein's equation because we need to look at the equivalence of mass and energy. And if you take these two equations and you substitute equation 2 in equation 1, you will get that force equals EA over c squared. That's force is the energy times the acceleration over c squared. But we know that E equals P times T. Energy is simply power times time, and we know that acceleration is velocity divided by time. So if we substitute these two equations in equation 3, we get F equals PV over c squared. Now, it's interesting now to look at the equation that we derived originally in lecture 1, which is that the reflection force F is 2P over c. Now you can see that this is similar to F equals PV over c squared, where you can see that breaks down into F equals P over c times V over c. Now the introduction of 2 into the equation for a reflected wave is simply because not only do you have the force in the wave itself, but you have to take into account the force, the reaction force, when that wave is reflected without any loss. If the plate was completely absorbent of the power being transmitted into the plate, then it would be simply F equals P over c. But because it's being reflected with no loss, it is F equals 2P over c. Now we've said that the velocity of the wave that's arriving at the end plate of the cavity is Vg1. So the force at plate 1 is 2P Vg1 divided by c squared. And again, you can see this is 2P over c, the basic equation that we've derived earlier, times Vg1 over c. Now, if we have two plates and we take the difference in the force on these two plates and we call that thrust T, we can see that T is equal to 2P over c times Q, where Q is the number of reflections that are taking place, times the force from each pair of reflections, which is Vg1 minus Vg2 over c. So we end up with this basic thrust equation, and we simplify it by saying that Vg1 minus Vg2 over c is equal to dF, which is the design factor. So the fundamental thrust equation for static thrust from an EmDrive cavity is T equals 2pq over c times dF. In slide 1, we derived an equation for thrust in terms of dF, where df, we said, equals vg1 minus vg2 over c. So these are guide velocity terms. In practice, it's much easier to design an EmDrive cavity by not using guide velocity, but by using the guide wavelength, lambda g. And we find lambda g, we relate lambda g to Vg by the equation Vg is equal to c times lambda naught over lambda g. Lambda naught is the free space wavelength, and it is found by simply dividing c by the frequency that we're operating at. So lambda naught is equal to c over f. But in the waveguide, lambda g, which is always longer than lambda naught, is equal to lambda naught divided by the square root of 1 minus lambda naught over lambda c all squared, where lambda c is a very important parameter called the cutoff wavelength. So what does cutoff wavelength mean? Well, it means that as the dimensions of the waveguide, or the dimensions of the cavity, decrease, we know that the velocity also decreases, but the guide wavelength, lambda g, will start to increase. And this will increase, lambda g will increase until it reaches this so-called lambda c cutoff wavelength. Now, in a standard waveguide which has a width of a, then the cutoff wavelength lambda c is equal to 2a. Now, this is for a rectangular waveguide and a TE10 mode. So we can derive the thrust equation using df, and we now can see that df can be expressed in terms of guide wavelength rather than guide velocity. The calculation of cutoff wavelengths for different transmission modes is rather more complicated. So what do we mean by transmission modes? Well, in waveguides and cavities, the mode of transmitting the electromagnetic wave, they're divided into two types of modes. That's the transverse electric, TE, and the transverse magnetic, TM modes. In a TE mode, the electric field is always transverse to the direction of propagation along the z-axis. Now, in a rectangular waveguide, it is therefore directed across the width of the waveguide, whose dimension is designated A, whereas the height of the waveguide is designated B, and this is the direction of the magnetic field. For TM modes, the electric and magnetic fields are rotated 90 degrees about the z-axis. And to help in the definition of the transmission modes, we use two designations which include subscripts N and M. In a rectangular waveguide, the designation becomes TEMN for a TE mode, or for a TM mode, it becomes TMMN. In circular guides, these definitions are TENM or TMNM, and you notice the switching round of the subscripts M and N between the two types of transmission mode. In a rectangular waveguide, the cutoff wavelength can be determined by lambda c, which is a cutoff wavelength, equals 1 over the square root of m over 2a squared plus n over 2b squared. And you can see from this formula that we are now able to relate lambda c, which we've said is a very important parameter, to both the dimensions of the waveguide, A and B, and the definition of the transmission mode, which includes the subscripts M and N. For a circular waveguide, the determination of the cutoff wavelength is slightly easier in that lambda c is equal to kmn times d, and knm is given by the table shown below, where knm is defined for the lower orders of m and n, where n equals 1 or 2 and m is equal to 0, 1 or 2. These lower orders of transmission modes are what we tend to use in an EmDrive cavity. So once again, we are now able to relate the cutoff conditions by determining the diameter at which cutoff occurs, dc, which is equal to lambda naught over k nm. The diagram illustrates a typical tapered EmDrive cavity, and in this case the end plates are separated by an integer number of half wavelengths, and that number is designated P, and the fact that there is an integer number of half wavelengths means that the cavity will actually resonate. The EM wave itself is typically shown as an E field, and you can see that the sinusoidal waveform starts to stretch as the diameter decreases as the axial length from the large end plate increases. The cavity that is illustrated here has actually 3 half wavelengths, and therefore for a TE01 transmission mode, the cavity itself would be designated as a TE013 cavity. We've said that the equation for guide wavelength lambda g is lambda naught over the square root of 1 minus lambda naught over lambda c all squared. And if you actually solve this equation, you'll find that it results in a very nonlinear change of guide wavelength as the axial length increases along the tapered cavity. And the plot that you can see there shows this. In fact, you can see that as the small end plate is approached, as we go along the increasing axial length, then the guide wavelength actually tends to infinity. I mean, it becomes almost a vertical straight line in the plot. This means that the guide velocity, which is governed by c lambda naught over lambda g, is going to approach zero as lambda g approaches infinity. Indeed, if the cylinder diameter goes below the cutoff diameter at a fixed input frequency, then the transmission of the electromagnetic wave itself completely stops. It's quite a useful effect, this, because in a domestic microwave oven, the mesh which is incorporated into the transparent door of the oven has sufficiently small holes in it to be so far below the cutoff diameter that you get an absolute cutoff of the electromagnetic waves which are bouncing around inside the oven. And these are very powerful electromagnetic waves. I mean, they can cook a chicken in a few minutes. So you really don't want these leaking out. Otherwise, we'd have a population suffering from cataracts. So we'll now look at wave impedance of a transmitted electromagnetic wave. This is an important parameter because to actually get power into an EmDrive cavity, you have to match the impedance of the tuned input circuit to the cavity itself by matching the impedance to the wave impedance of the electromagnetic wave, of the wavefront of the electromagnetic wave at the position that the input circuit is along the axial length. Now, the equation for a circular cavity, the equation for the wave impedance, is given by ZW equals 376.7 times the square root of 1 minus lambda naught over d times KNM, where d is the diameter at the axial position at which you're determining ZW. And if you look at the plot of guide wavelength, which is given in ohms, as all impedance is, against the axial length along the tapered cavity, you will see that as the diameter approaches cutoff diameter, in other words, as we reach the cutoff point along the axial length of the tapered cavity, when you actually reach the cutoff diameter, wave impedance approaches zero. Now, we've already said that at this point the transmission of the electromagnetic wave stops, and we can see that also the wave impedance at this point is zero. We've seen that the cavity Q factor is important in determining the thrust from an EmDrive cavity. The thrust, specific thrust of a cavity is indeed directly proportional to the Q. And the Q itself is dependent on the cavity volume. So the Q goes up as the volume goes up, and on the surface resistance of the walls. And if you look at the equation for the theoretical unloaded Q of a circular cavity, you can see it's a somewhat complex empirical equation, but if you look at the first term, which is 377 divided by 2RS, you can see clearly that the Q is going to be inversely proportional to RS, which is the resistance of the walls. The volume of the cavity is also important, and you can see in the equation L0, which is the axial length, dm, which is the mean diameter, and a considerable number of other factors which end up with giving you the unloaded Q of the cavity. Now, the unloaded Q is in fact the natural Q of the cavity, assuming that there are no other loads which will reduce the Q. Now, if we look at the surface resistance, then this depends very much on the material of the walls, the temperature, and the frequency at which it is operated. And the Q of a cavity can actually vary between 10 to the 4th for a normal room temperature copper cavity to as much as 10 to the 9th for a superconducting cavity operating at very low temperatures. If we look at the value of the surface resistance, you can see that it equals the square root of pi times the frequency times mu r mu naught divided by sigma. U naught is the permeability of free space, and mu r is the relative permeability, and sigma is the conductivity at the operating temperature. And if we look at a superconducting material, it's applied to the inside of the cavity as a thin film, and the material we use is yttrium barium copper oxide. You just refer to it as IVCO. And if you look at the surface resistance, which is shown in the graph on the left, then you can see that between 10 degrees K and 70 degrees K, there's a fairly low slope of the resistance going down as the temperature goes down. But around 70 degrees K, there is a critical point where the resistivity suddenly goes up as the temperature goes up. So clearly what you need to do is to operate this material below the critical temperature. Now, 70 degrees K is around the boiling point of liquid nitrogen, so it means that you can actually run a superconducting cavity using IVCO thin film on the internal walls by really just bringing it down to liquid nitrogen temperature. However, if you go down to liquid hydrogen temperature, which is around 20 degrees K, then not only do you get a lower surface resistance, but as the liquid hydrogen boils off to maintain this low temperature, then you can use the cold gaseous hydrogen in a fuel cell to produce the electricity which will eventually produce the microwave power for the cavity. So now we look at what loading a cavity actually means. And the biggest loading that you get on a natural cavity is the input circuit. And this input circuit can take the form of a slot in the wall of the cavity, a probe poking through the wall of the cavity, or a loop that's mounted on the internal wall of the cavity. Now, whichever input circuit is used, you have the problem of matching the output impedance of the power amplifier to the wave impedance of the cavity. So if we look at the block diagram, you can see the power amplifier feeds into the input circuit, which must have an input impedance of 50 ohms to match the standard output impedance of a power amplifier. And the Q at this point, as we're looking into the input circuit, is actually the loaded Q of the cavity, QL. Now the output impedance of the input circuit has to match the wave impedance of the cavity itself. So looking into the cavity, Zin must equal ZW, the impedance, wave impedance of the electromagnetic wave which is transiting up and down the cavity. The important thing to note, however, is that this input circuit, which has this impedance matching requirement, must also be a high Q itself. And we designate the Q of the input circuit as Qi, and this actually must equal the unloaded Q of the cavity, Qu, to ensure maximum power transfer. This is quite a significant requirement on the input circuit, and almost inevitably it means that that input circuit itself must be able to be tuned so that you can get this good match between the output impedance of the power amplifier, if you like, and the wave impedance inside the cavity, as well as ensuring that the Q of this input circuit is maintained to be as close to the unloaded Q of the cavity as you can get. In this situation, we then have a method of determining the loaded Q of the cavity, and this is actually given by the equation 1 over loaded Q equals 1 over the input circuit Q plus 1 over the unloaded Q, the natural Q of the cavity. And you can see from this equation that for a correctly matched system, basically where QL equals QU, where QI equals QU, then the loaded Q, QL, is equal to half the unloaded Q of a cavity. We'll now look at a selection of cavity geometries which have been used in EmDrive thrusters. And the first thing to define is that the Q factor can actually be viewed as the number of transits that the electromagnetic wave makes across the cavity from small end plate to large end plate, whilst it maintains the input energy level. The reality of any cavity is that the number of transits are far higher than this, but of course they have a continuous drop in energy level as the losses in the cavity walls take place. Now, the important point about the shaping of the end plates is that if you think about a truncated cone with flat end plates, you will obviously have a longer path length along the wall than at the centre of the cavity. I mean, it's pretty simple geometry, this, but it does seem to have escaped the notice of one or two experimenters who have found that they really can't get a high Q cavity at all with flat end plates. It's important to maintain the same path length between the points, the corresponding points on the small end plate and the large end plate. Otherwise, what happens is that you get a significant phase error across the wavefront. And if this phase error is allowed to build up, it very rapidly destroys the Q of the cavity. So we've said that obviously the end plates of a truncated cavity cannot be flat. And figure 1 shows the simplest of solutions to this, which is where you have the wall length shown as R1, where R1 is part of a radius back to an imaginary 0 point, such that the radius is maintained across the wavefront, and R1 is maintained constant simply because it is defined by the radius from the imaginary 0 point. This is the simplest of geometries to think of for maintaining the constant path length, but it's not the easiest to manufacture. Figure 2 shows a geometry that we've used on a number of thrusters that is much easier to machine, and it also enables easier alignment of these end plates, which is, as we'll see later, an important factor. What we have here is a flat small end plate and a large end plate which has a flat central proportion and an annular rim section which has a constant radius R2. And so we see that in this case as well, we will be able to maintain the same path length between corresponding points on the small end plate and the large end plate. Now, figure 3 shows a particularly interesting geometry, which is useful for superconducting cavities where you want just the large end plate to be superconducting, and this is more easy to achieve if indeed it's a flat end plate. However, if you're going to have a flat large end plate, the surface of the small end plate requires quite a complex curvature, which you can calculate, but it needs extremely good machining tolerances to maintain the Q of this particular cavity geometry. However, as I say, it has the advantage of using a flat large end plate, which is where the majority of the energy loss will take place, and it's that particular large end plate that you want to maintain the minimum value of surface resistance. So the final factor that we should take into account when designing and manufacturing an EmDrive cavity for a thruster is the dimensional tolerances of the manufacturer of the cavity itself. And if you're going to get a very high Q value, it means that the dimensions of the cavity itself must be machined to very small tolerances. This again is to minimize the path length differences across the wavefront. We've said they create phase errors, they lower the Q, and interestingly they widen the effective bandwidth of the operation of the cavity. Now, if you look at the plot shown on the left, you'll see how the measured Q of the cavity varies with the mean tolerance of the manufacturing techniques used. This was not an easy set of experiments to do, but we were quite pleased to get consistent results. And you can see that if you start off at the theoretical Q of around 74,000 for this particular design, you drop down to 55,000, which was the working maximum value of the cavity at about 0.1 of a millimeter. We needed much better than that when we looked at the not only the manufacturing tolerances, but also the alignment of the two end plates. That again is extremely important. And you can see simply that if you don't align the two end plates, you're going to get differences in the path lengths from one part of the cavity to the other. What we aimed to do was to meet the specified tolerance for both the machining and the alignment of about 100 microns for a Q of 55,000. So the other thing that we mentioned that happens is as you increase the tolerance of the machining, the Q will go down, but the frequency tolerance from the source goes up, and we can in fact use a rather wider band frequency source to good effect, even though we have higher rather lower manufacturing tolerances. And this was very advantageous in the early days of experimental EmDrive, when we were actually making cavities out of sheet copper. And that's obviously very difficult to hold manufacturing tolerances very tightly when you're using this manufacturing technique. We were, however, saved because the source we used for our microwave power was a magnetron. And magnetrons have a wonderful ability to lock themselves to the main resonant component of the cavity, whilst producing a wide band output consisting of many spikes, which tends to fill in where the errors occur between the because of the manufacturing tolerance of the cavity that you actually make. This can only be actually utilized to Q values of a few tens of a thousand. I think we got about 35,000 for the best cavity we manufactured from sheet copper. And certainly if you want to go higher than that, you have to use a narrowband source and high tolerances, or sorry, low machining tolerances when you manufacture the cavity. And this was in fact how we produced the SPR flight thruster. And the results you see in that graph are actually measured results from our flight thruster.